rectangular coil of n turns and an area A spins at constant frequency F in a uniform magnetic field of flux density B. Complete the table below to show how the flux linkage and the induced EMF relate to the orientation of the coil during one cycle of rotation. Alright, so here we go. First off, time is a little bit odd, so I'm going to have a look at that first. And basically they're saying time, for example, as our classic example, is 0.25 upon F. Now, what does that actually mean? Well, if you remember that T is equal to 1 upon F, that means 0.25 of a period. So basically, we're going up in units of 1/4 of a turn, or 1/4 of a rotation, because after 4 lots of their units, we've done 1 complete period, so 1 complete rotation. So we start off, and we've got 4 points we've got to consider. Now at time of 0, and my time here, I'll put 0, so my 0 time, the orientation of the coil is parallel to the field. So if I draw this, there's my north, there's my south pole, and my armature is in the middle, and I'm going to have that as the black wire, as the white wire. And then we're going to go and move across in terms of time. So we're then going to have 0.25 upon F, which we know then is a quarter of rotation. So I'm going to have it rotating in that direction. So north, south, now means that wire will rotate to the top, that will be at the bottom. Another quarter of rotation, and I'm going to have north there, south there, and it'll rotate it around to the next stage. And the final one there, 0.75 upon F, is going to give us north, it's going to give us south, and I've gone around, so now the white wire's made it all the way to the top, and the black wire's made it all the way to the bottom, because all of these are rotating the same way clockwise. So there we go, and obviously that will just continue through rotation after rotation after rotation. Now, the next bit they've given us is we've got to look at, we've got the orientation of the coil. Now to check this, they've said at time 0 we're parallel to the field, perpendicular to the field, parallel to the field, perpendicular to the field. So that works perfectly in terms of the position of our armature. The next thing they want us to look at is our flux linkage. Now our flux linkage is N phi, and our flux linkage is actually, that's going to be equal to BAN as our maximum value, because phi is your flux density times by your area. So that's going to be our maximum value we can have. So I'm just going to draw some axes and we'll have a look and see how this goes. So if I draw that across, this is going to be the time at 0, time at quarter of a turn, next turn, and next bit of a turn. And if I look at, they've told us, the first thing we want is the flux linkage. Now they've told us at a quarter of a turn, our flux linkage here is plus BAN, which is our maximum value. And that immediately makes sense, because can get the most field lines through the loop of this coil when I'm perpendicular to the field. When I'm parallel to the field, no field lines are actually going to pass through that coil, so that's going to be a 0. And again, parallel to the field, 0. Now here what I've done is I've got the same number of field lines, the same maximum number of field lines coming through, but the coil's the other way round. So here the black one was at the top, there's a bottom, so it's rotated through 180 degrees. Now we represent that by saying we've got minus BAN as the flux linkage at that point. Now I can draw these out, and I can make that into a nice smooth curve, hopefully. There we go. That's my nice curve. And again, that will just continue and continue and continue. Now if we look back at our formula sheet, what they actually give you on the formula sheet is your magnetic flux linkage, N phi, is BAN cosine of theta. Now, if I look at this, cosine of 0 is obviously 1. So here, my theta, that's my 0 degrees. Quarter of a turn, 90. Next quarter of a turn, 180. this must be effectively is 270, or you could write it as minus 90 degrees. So it's a little bit odd because they've defined time zero here when the angle we're talking about is minus 90 or 270 degrees. So it's a little odd compared to the formula you're actually expected to work with. So we've looked that far. Next bit we're going to look at then is our EMF that's induced. So if we're going to draw the same idea in terms of the axes, there's my axis go across, there's my 180, there's my 90, there's my 0, there's my 270 minus 90 degrees. And the EMF we're given, and we know, is so the EMF is equal to ban, I'm taking this directly off of your formula sheet, so ban omega sine omega t. Now you can actually write that, and the book likes to write that slightly differently, and what they write it as E is equal to E naught sine omega t. Now the idea of this is that E naught is your maximum value, and it equates to ban omega. So the maximum you get off there is basically going to be your ban omega. And that gives you your maximum EMF, which is E naught. Now they've actually told us at the first point at 0, what we've got is our EMF is, and they've said up here, we've got a value of plus E naught. So we've got E naught actually there. So that's our value at that point. Should have drawn these as lines rather than crosses. So there we go. Now, if that's our maximum, obviously our minimum is going to be minus E naught because it goes through this sine function. And we can, first thing we could do is just do it in terms of the rate at which we're cutting field lines. So at this point, we're cutting the field lines maximum. If you can imagine, the field lines here are all horizontally, so I'm moving vertically down at this point. I'm perpendicular to the field lines, I'm cutting the field lines at a maximum. At this point, the field lines are horizontal. I'm actually, these wires are moving horizontally at this point, therefore I'm cutting 0 field lines. If I'm cutting 0 field lines, I'm going to be inducing 0 EMF. I'll put circles around them to make them a little bit more distinct. Here, I'm cutting maximum field lines again because I'm going up and this one's going down, but it's reversed. So what I'll be inducing here is minus the maximum EMF. And here again, I'm horizontal, so I'm moving horizontally. I'm not cutting any field lines. So again, this is going to be back to 0. So I can draw a nice little curve on that. Here we go. Take it down, take it across, take it back up here. So I've got values of plus E naught, 0, minus E naught, 0. And that's just done through the kind of logic of how many field lines am I cutting at each of these stages, or the rate at which I'm cutting the field lines at each of these stages. Now the other way of doing it is obviously there's a relationship, because your EMF here is minus n d phi by dt. So if I differentiated cosine, I get minus sine. The two minuses cancel out, the minus sign and the EMF actually being minus n d phi by dt. So what I end up with is saying, well, the gradient's biggest and positive here, so it must be the biggest positive EMF here. So biggest and positive gradient, biggest here. 0 gradient here, say 0 induced. Biggest negative gradient here, so negative EMF induced. 0 gradient here, 0 at this point. So that fills our points across the board in terms of our induced EMF. Hopefully that makes sense. Thank you very much.